Hello everyone, this is Professor Iris Miano speaking to you in pre-calculus class. This is Math2 Day12 material. Today we will be very ambitiously covering two sections, one on one-to-one functions and their inverses, and the next section after that will be on exponential functions. Quite a bit of material to cover today. We won't be able to get into every single possible scenario that you'll encounter in homework, but that's what we have class for. So make sure that definitely once you've viewed this lecture and you're getting started on homework, that you make special notes about some of the things that you'll be seeing in the homework set that are not explicitly shown here for the sake of time. Okay, but let's get started in section 4.2 on one-to-one functions and their subsequent items, inverse functions. So we want to first look at the definition, which of course I pulled straight from your textbook, so everything is, has a lot of continuity here. A one-to-one function is of any two different inputs in the domain. They correspond to two separate outputs in the range. So, and there's some function notation associated with this as well. The way that we want to think about this in a qualitative sense or a visual sense lends itself really nicely to the figures. So notice in figure 6 here, directly underneath the definition, we have a list of inputs here in pink, and each individual one maps to a very, distinct output in the range, which is right here in blue, okay? So this one's easy to see that the function is one-to-one because for every one input there's one output. They connect straight away. There's not even any crossings of between inputs and outputs as far as the listing is concerned. It's just one input straight to one output, done deal. It fits what we could even very much in a surface way be able to interpret what a one-to-one function is, what the definition of this term is. Now notice in figure 7, we have a function being exhibited here with the domain being in pink and the range being in blue, inputs and outputs respectively. But notice that we have two inputs mapping to the same output. Now, this is still representing a function here, but it is no longer one-to-one because we have two separate inputs going to the same output. So there's no distinct output for every single input. So hopefully that makes sense. And if we need a little bit more of a representation of what's going on here, some more visuals, we can look to figure 8, which is a three-parter. Part A is showing us a very quintessential, very straightforward representation of a one-to-one function. We have each of the three inputs shown, x1, x2, x3, mapping to one particular distinct output, y1, y2, y3 respectively. This one's a one-to-one function being exhibited here in part A. In part B, we still have a function being represented as far as the relation between the pink input and the blue output, but it's not one-to-one because as you'll notice, x1 and x2 map to the same output of y1. So it's not one-to-one, but it's still a function. And then furthermore, to remind ourselves of what it means to be a function, in part C, we see an example of something that's not a function, in which we have one input in the domain, the pink area right here, mapping to two separate outputs in the range, okay? So that'll give us an instance in which we see a relation that's not a function. Now, going back to this idea of being one-to-one, is there a way graphically that we can test this out? Indeed there is. It's called the horizontal line test. So if you recall, the vertical line test was used to determine if a relation was a function. So now we have the horizontal line test, which is to determine if a function is one-to-one. So if at any point in your trajectory, which we have in blue here for figure 10, the two different graphs in figure 10, in part A, we have the blue trajectory being crossed twice over by a representative horizontal line at y equals 1. So since there are two crossings of a horizontal line, since that is possible for the trajectory of the function here, that means that it is not one-to-one. However, so this is y equals x squared. y equals x squared is not 1 to 1. It is a function, but it isn't 1 to 1. It fails the horizontal line test. Enter the cubic function, though, y equals x to the third power. Notice that every possible horizontal line that could be graphed on top of this blue trajectory representing this graph, it only crosses the once. So this would be an example of a function passing the horizontal line test, and if it passes the horizontal line test, it is 1 to 1. Okay. Now a function can be considered for just a particular interval on its graph, and then you can say as long as it's just increasing on that interval, then it can be 1 to 1 just on that interval. So for instance, going back to figure 10 part A here, if we're just considering this y equals x squared relation from, let's say, 0 off into positive infinity, or anywhere out here, say from 0 to 2, for instance, on this interval right here of what we can see, we would say that within that interval, the function is 1 to 1 because it's only increasing on that interval. And the same is true if it's only decreasing on the interval. That's another way that you could say that at least on the interval, a function could be considered to be 1 to 1. But as far as a function's 1 to 1-ness for its entire trajectory is concerned, the horizontal line test will either confirm or deny the 1 to 1-ness of the function. It'll confirm that it's 1 to 1 if the graph passes the horizontal line test, like we see in y equals x to the third power right here. Or if it doesn't pass, then we say that it's not 1 to 1. Still a function, though. Okay, we have a few examples here that I want to get through. So here are some fresh relations. They're all functions, actually. We can say that definitively. Indeed. So these are indeed functions, but are they 1 to 1? That's what we want to figure out. So 13, the example there, we have domain and range values in hours and dollars respectively. And as you can see, for each input in the domain, there's exactly one output, and you go just a straight line across to get from one to the other. So this one is so very clearly 1 to 1 for number 13, okay? For number 14, notice that the trajectories from the domain values to the range values, they do have a crossing, but pay that no mind. What you're really looking for here is, does each individual item in the domain map to a distinct item in the range? And that is certainly the case, even though these first two cross wires here, going from the domain mapping to the range, that doesn't matter. What matters is that each distinct item in the domain maps to exactly one distinct item in the range. So that is the case here for number 14. So number 14 is indeed 1 to 1 as well. How about number 15? Well, notice we've got each item in the domain. Oh, it doesn't. They all don't map to a distinct value in the range. Notice that 20 hours and 25 hours each map to the $200 in the range. And since they map to the same value, we say it's not 1 to 1. Okay. And then similar thing is happening here. It's just we have the last two in the domain seem to be mapping to the same value in the range. These number 15 and 16 still functions, mind you, but they're just not 1 to 1. Okay, very good. Now moving on, more examples. And this time we're going visual with it. Okay, so we're given numbers 21 through 26. And we want to see if they are representing 1 to 1 functions. And we can use the horizontal line test to do this. So notice that I have my little horizontal line off to the side here. Okay, so if I want to, I can just kind of scan it from top to bottom, and if there's at any point in which the blue trajectory crosses this green line more than once as I scan, then I will say that it's not 1 to 1. But if it only crosses the one time, like we see here in 21, we will call this 1 to 1. Okay, how about 22? Let's scan that one. Pretend you're a robot. Scanning, scanning, scanning. It only hit the once. All right, so number 22 is also 1-to-1. What's going to happen with number 23? You guys see it coming? Look at that, scanning. Oh, right away. Look, I have two separate instances in which it crosses, right? So that means it's not 1-to-1. Perhaps this is getting painfully obvious now, but let's go ahead and continue on this. In fact, I'm going to go ahead and leave that one there. I'll copy it though, so I can play around with this a bit more. There we go. Scanning for number 24. Scanning, scanning. Oh, check that out. Not 1-to-1, because look, crosses 1, 2 spots. Again, I will copy that. Number 24. Let's go ahead and just give myself that right there. Cool. Scanning for number 25. Seems to only be crossing once. Now I know you might be thinking, well, isn't it going to get completely horizontal in the case of where it's going to ride that asymptote? Technically, no. So we'll get to say that 25 is a 1-to-1. It's getting infinitely close to the y=0 line or the x-axis line, but it's not actually formulating it. However, looking at number 26 here, as soon as I hover that green line directly over the blue line, there are actually infinitely many points of contact going on right here, right? So it only needs to cross twice in order for it to violate the horizontal line test. So we would say that any horizontal line is not 1-to-1. Okay, great. Now we're going to get into this idea that 1-to-1 functions gravitate towards, and that is coming up with the inverse of a function. So if a function is 1-to-1, it necessarily has an inverse. And what is the function's inverse? Well, it's basically the function's mirror reflection over the y=x axis. If you're thinking about it graphically, it's also a version of the function in which the domain and the range are switched. It's kind of like that function's bizarro world counterpart, if you will. Okay. So here are some features of functions and their inverses. If you're talking about the domain of f, a function, then the range of its inverse will be exactly equal to the domain of the original function. And by the way, we have this symbol, the f to the -1 power. It's not that we are taking the reciprocal of a function necessarily. This notation denotes inverse, not necessarily reciprocal. Okay, and furthermore, the range of the original function f is going to be equal to the domain of the inverse of f. And then you can compose functions and their inverses inside of one another, and they will settle down once you simplify that function composition. It will simplify down simply to an x, which is, again, at y=x, or f of x=x, is going to be the line of reflection over which you will see a function and its inverse will be having that relationship when you graph them on the same set of axes. Okay, cool. So if we're talking examples here, which of course we should, let's find the inverse of the 1-to-1 function for number 27 here, okay? So we'll state the domain and range of each inverse function, or of, yeah, the inverse function. So the inverse will be switching the two, basically. So we'll have annual precipitation. I'll kind of shorten it up a little bit, which will be the 49.7, 43.8, 4.2, 61.9, 14.9, and we will have, that is the inputs now, so talking about the inverse. Oh, sorry, I already wrote inverse. LOL. Get rid of that. Inverse is right here. So this is it. Annual precipitation, and that's going to map to the location, which will be Atlanta, Georgia, Boston, Mass, Las Vegas, Nevada, Miami, Florida. So you can just write these items in the same order that they're given. Los Angeles, California. And instead of it being mapped location to precipitation, we're going precipitation first and then map it to its location. So this is how the inverse will look as far as the this chart-ish representation is concerned. And then the domain and the range. So basically this is now the domain. You would just list these items, and this will be your range of the inverse. So the range of the inverse was the domain of the original function, and the domain of the inverse was the range of the original function of inverse. Okay, great. Now let's go ahead and practice the algebraic business here, which is to say, if we have a function and supposedly it's inverse, how can we confirm that those two are indeed inverses of one another? Well, you can do the following. Hold on just a moment. Yes. Let's go ahead and take these function compositions happening right here. So I kind of wrote on top of it here, so try and disregard that. We want to verify that the function f and g are inverses by showing that f of g of x is eventually going to equal x. But let's go ahead and do this function composition. We'll do the same for f of x inside of g of x as well. All right, so first we'll have 3, because that's the f of x, minus 2 times the input. Now the input is no longer just an x, like it is here with f of x. The input is now g of x. So put the entirety of g of x inside of these brackets here, which is 1/2 times the quantity x minus 3. Okay, so then the thing we want to do here is distribute, or rather just multiply inside with the negative 1/2. Why do you want to do this and not distribute all the way through? Well, you'll find that negative 2 and negative 1/2 are, multiplicative inverses of one another. So when you multiply them together, you're going to get a 1, which is kind of cool because it just kind of, as a multiplier, just kind of cancels out. Okay, so then what we have here is 3 plus, and then you'll still have the x minus 3 technically in parentheses, but at this point you can kind of, get rid of those. And notice that the 3, positive 3 here and the subtracted off 3 here are going to cancel, and you'll just be left with x. Okay. So hopefully everybody can follow the algebra there and feels good about it. If you want to talk a little bit more about it in class, certainly we can. I'll do the other end of it though. Let's say that we fed f of x inside of g of x. What should we expect to get? Well, we'll take a g of x structure, negative 1/2 times the quantity of, what is it, x. And let's, instead of x, what are we putting in? 3 minus 2x, right? And then minus 3. So yeah, kind of give myself a little bit of a barrier here for the rest of my work. Notice that I really don't need to have these brackets here after the fact, and this 3 and this negative 3 are going to cancel out. So it's really like I have negative 1/2 times negative 2x. These, again, like we saw in the previous iteration here, are multiplicative inverses, so you know they'll cancel. Let me actually just do this with the green because it will really look nice, and we'll just be left with the x as desired. So we have two different instances, right, of some function composition with two functions that were said to be inverses of each other, and the way that we're confirming this is by composing them into one another, so g inside of f and f inside of g, and in simplifying both we find that they settle down to just simply a value of x, which is what you want. Okay, if indeed f and g are inverses, and that's what we were tasked with doing, we wanted to verify, and indeed we did. Okay, moving on to the next set of examples here. Excuse me, let me roll this down a little bit. Okay, so we're given several, and I want to do these relatively rapid fire here, several different examples of functions, and the y equals x line is also graphed in the same coordinate plane. So what we want to do is understand what's going on with the function inverse and graph it on top of what's already presented here for each coordinate plane for numbers 45 through 50. Okay, so I'm going to do it in green, so it's a pretty good contrast to, or you know what, I'll make it in orange, so it's like a real nice contrast to the blue there. And I'll just graph all of the points and trajectories of the inverse here in orange, okay? So notice that this point -2, -2 on the original blue trajectory, I mean it's in black, but it's a point that's on the original function here. If it's on the y equals x line, it exists not only in the original function, but also the inverse as well. So I'm going to just put a little orange dot right there. Whereas the next plotted point, if I just move my trajectory up, is -1, 0. So that means switch the x's and the y's because a function's inverse, the domain and the range are just switched. And we can plot the next point in the inverse, which I'm doing here in orange. The inverse I'll do in orange. So that'll be at, if a -1, 0 exists in the original function, then 0, -1 exists in the inverse. Similarly, 0, 1 is on the original function, so 1, 0. You guys can probably see where I'm going with this. And then 1, 2 exists in the original function, then the inverse has 2, 1, which is 2, 1 right here. About. So we can connect these dots here to the best of our ability. I mean, it'd be great if we used a straight edge, but I don't have one. So, you know, take what I'm drawing here with a grain of salt. But if I had drawn these perfectly, you would see with the orange, it would be a direct reflection over the y equals x axis, which is a feature indicative of functions and their inverses. So we'll do this relatively quickly for the rest of the trajectories as well. So again, this point for number 46 is on the y equals x axis, so it exists in the function and the inverse. 0, -1, so -1, 0 has to be on the inverse. 1, 0, 0, 1, and then 2, 1/2, we have to go 1/2, 2, which is about right there. Connect those dots, boom, 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 and we have more or less relatively rough but a reflection over the y equals x axis. Now when you have curvy bits, like what we're going to see in numbers 47, 48, 49, and 50, you're really just trying to reflect over the y equals x axis with not so much in the way of points. Well, there are points for 47, 48, so we do have some gauge here. And again, notice that this first point on the original function is on the y equals x axis, so then will be the inverse point. And then what does it do? The blue trajectory, I mean. Just going from -1, -1 to the origin, it kind of, you know, swoops up and does this little curvy bit. So we want to do the reflection, more or less, over the y equals x line, and then come back around to the origin, which is on both the original function and the inverse. And then the trajectory for blue ends at 2, 1. So for orange, it should end at 1, 2, which is right here. And it should curve up more or less like this. Again, when you're drawing a function's inverse, you want to have it be a reflection of the original function if you're drawing everything on the same set of axes. Okay, and we'll use these beginning and end points as reference when we tackle number 48 as well. Hold on, let me get rid of that marker. Okay, so if the original function has -2, 1, then we should go 1, -2. So where's 1, -2? Well, it's right here, right? And then the other end will be at 1, -1 for the original function. So -1, 1 should be the end of it here. So like right there. Okay, and how does it go? Well, we start off more or less horizontal but dip down. So go vertical but dip down to the origin. Want to meet up at the origin. And then kind of go down and up. That one's really rough. Let me try that one again. Whew, that is hard to do with the stylus. Okay. So... okay. Not my best artwork, but I think you guys get the picture. Ultimately, the final goal is always going to be drawing the mirror image over the y equals x, this diagonal line. It's in every single one of these coordinate planes for a reason. That's where the line of reflection is. Okay, so now for 49, notice that we cross the y-axis at what? 0, 1. So at 1, 0, we should be crossing right here, the x-axis. And we should treat this trajectory here as writing this, y equals 0 asymptote. So we should have the x equals 0 asymptote for this orange trajectory and kind of curve in the same manner that we see in the blue, but for the orange. Okay, so I'm going to try my best here to just go through, and yeah, more or less it looks like that. Again, not great artwork, but you get the picture. Lastly, number 50 is going to be the most challenging, but notice that there are 1, 2, 3 points of intersection with the y equals x line. We're going to use that to our advantage and just kind of go on the opposite side and cross here, go back up, kind of loop-de-loo, and have the same arrow points on either side. little bit rough there, but I think you guys get the idea. And when you're doing problems of this ilk in your online homework, of course you'll have the graphing utility to work from, and it'll be way cleaner and nicer looking. Just wanted to give you guys a basic idea of what it means to look at a function and its inverse. It's always a reflection over the y equals x axis, which is a very quintessential diagonal trajectory, diagonal trajectory that goes through the origin. Okay, now let's talk about inverses and finding them algebraically. So there's a 3-step process that we want to go over here, in which we will basically let y equal the function value. So you know how we've been using function notation f of x. Go ahead and, as a step 1, replace that with a y. Y is just easier to work with function as like algebraically than the function notation. And then you're going to switch the x's with the y's, and you're going to solve for y at that point, and then replace that y with the f inverse of x. And once you do that, you are looking at the function inverse equation. And there you go. So here's what we're going to do. Okay, just a moment. We are going to find f inverse. Okay, so we're given a 1-to-1 function f of x equals 4 over x plus 2. We're going to go through the 3-step procedure in order to find the inverse, and then we're going to graph, we're going to find the domain of f and f inverse, and we're going to graph both of them and y equals x on the same coordinate axes that you see already given to you to the right. Okay, so let's waste no time. Let's go ahead and first replace f of x with y. So at this point, we want to, what I usually do is draw a line, and then now you're talking about the inverse underneath this line, so maybe we'll even change the color. So from here on out, we're talking about the inverse in the act of switching the x and the y. You see how this is like a totally different equation now? I switched the position of the variables. So that's not what now makes it the inverse, okay? So here we go. Let's go ahead and now solve this guy for y. So what you will get to do here is multiply both sides by y plus 2 and simultaneously divide both sides by x. So essentially, you can, and I know this is going to be a little jarring for folks, you can switch these guys, the numerator of one side of the equation, and yes, I did throw it over a 1 to make it like forced to be looking like a numerator. You can switch that with the denominator of the other side. It's the same thing you'll get if you go through the motions of, like I said before, multiply both sides by the quantity y plus 2, and then also divide both sides by the quantity x. So in doing so, we will be left with the following. Y plus 2 was supposed to be a y plus 2 is equal to 4 over x. So now we need only subtract 2 on both sides. Subtract 2, subtract 2. It'll get rid of it here. Huh? Hold on just a second, guys. Okay, we're back. I just had to tuck in my kid real quick for her nap. She's good to go. All right, so where were we? We were subtracting 2 from both sides, and that's going to give us our function inverse. So that'll be now y equals 4 over x minus 2. But it's not in the appropriate notation, right? So we need to take the next step of actually putting this in the appropriate notation, which will be not f of x, but f inverse of x. This little exponent of -1 that on a function notation indicates an inverse. So that'll be 4 over x minus 2. So it'll be a reciprocal function with scalar and a little bit of horizontal shifting, right? Okay, so that's something that we can expect here. Now, before we get too deep into the graphic, let's talk about the domain of f. Is going to be x cannot equal 2. The range of f is going to be that y cannot equal 0, right? Because we have the whole thing going on here. With that, if we recall from our reciprocal or rational function days, and then the domain of f inverse is going to be exactly the, the range of f. So maybe I'll put even like a little bit of a line from here to here. It'll be that x cannot equal 0, right? And the range of f inverse is going to be that y cannot equal 2. Or sorry, -2. -2 is what I meant to put here. -2 and -2. And that'll be, there's a connection here because when you're talking about a function and its inverse, the domain and the range switch. Okay, great. So that's all of that stuff. Now we can start talking about the graphic. So I did a little sneaky thing here where I have it in layers. Okay, so here's your coordinate plane. Let's go ahead and just start by graphing the original function here in red. Okay, so that's your y equals, or f of x rather, equals 4 over x plus 2. So as you can see, it's that rational function kind of a deal here where we have a horizontal asymptote at y equals 0, right? That's associated with our range missing values there. And then our vertical asymptote is at x equals -2. Now, go ahead and make sure we have the y equals x line because we're going to reflect this red trajectory over this blue y equals x line in order to see what the inverse function looks like. That's your 4 over x minus 2. And that's what that looks like there in green. And as you can see, it's just got beautiful symmetry over the y equals x-axis as far as the red and the green curves are concerned. Okay, great. So that's that on this one over here. And so since these are rational functions, the original function and its inverse, so hopefully we have a relatively easy time graphing those based on the stuff that was presented back in the last unit. All right, cool. Moving right along. All right, let's get deep into exponential functions, and we're just going to touch on some things here. We're not going to get as deep as we could, just because I don't want to make this too dense of a lecture. I just want to warn you guys that there could be more to this discussion, and we can dive into whatever we think is pertinent for further discussion when we meet in lecture. Okay, so the first thing that we want to do with introducing exponential functions is revisit these laws of exponents. So you'll notice the first one here that I'm going to put a star next to is the product rule for exponents. So if you have a product of two exponential expressions with the same base, you get to add the exponents together to find the resulting product. Right here, this next one that I'll put a dot next to, that is the power rule, which is to say that if you have an exponential expression raised to a further power, you'll multiply the exponents to get the result. If you have a product, now I'm talking about this one here with the x next to it, inside of a base of an exponential, then it's kind of like you distribute that exponent, in this case of s, to the individual factors of the product. 1 to any power is just itself 1. If you have a negative exponent, it can be rewritten without the negative sign by throwing the exponential expression, so to speak, in the basement, or you could raise it, the entire 1 over that base to the exponent itself. It has a couple of different representations depending on what you want, and anything non-zero, that is, raised to the 0 power is going to be equal to 1. So that's a 0 exponent rule there. Okay, so just a little bit of an overview of some laws of exponents. And yes, and so here is the definition of an exponential function. It has the form of capital C times a to the x power, where c cannot be 0, otherwise it would just, it'd be f of x equals 0, and that's no fun at all. A needs to be positive. It cannot be equal to 1, because that would be super boring. 1 raised to any power is just itself. So we have these stipulations to make it possible and also not boring for our particular exponential function. And so what else does it say here? The domain is set to all real numbers, and that goes for every exponential function, okay? The base A is a growth factor, and so the C value is the initial value. It's also the y-intercept, provided that there hasn't been any shifting around of the exponential function, okay? So here, next, I just have lifted from your textbook an f of x table of like one of the most rudimentary exponential functions that there is, 2 to the x power being that particular one. So you'll notice that as the x values for this function are negative and getting more and more negative, the output value is extremely small. And so that tells you that as we go off to negative infinity in the x direction, so for movement to the left on the x, or in the coordinate plane rather, you're going off to 0. So you're approaching 0, the limit of this function, therefore, as it x approaches negative infinity, the output of that is going to approach 0, okay? And so in that case, we could say that this trajectory, as it moves in this direction to the left, it's going to start to ride the y equals 0 line here, the x-axis. It uses it as an asymptote, and it's never going to cross, provided, of course, that we're talking about exponential functions that are not shifted in any way. Now, what else can I tell you? This curve is going to have what's called a pivot point. I guess the textbook doesn't really talk about it that way at this point, but at its y-intercept, and then that's when the growth factor is really going to shoot up, and it's going to have the trajectory of this exponential function really shoot up and grow at an incredible rate, growing exponentially. I mean, haha, it's kind of like the cliche way to describe what's going on here, but it's cliche for a reason. It just grows really super fast after a certain point, okay? So if we are just looking at a table of values, you can actually determine if the function in question is exponential just by looking at its inputs and outputs, as long as you're looking at some consecutive inputs, that is. And therein lies this theorem right here. For an exponential function, f of x equals c times a to the x power, as long as a is positive and not 1, and we have consecutive outputs being put in a ratio, this value a should be constant for any consecutive output, or inputs rather. The outputs should also have the same ratio. Okay, so I have highlighted a few examples that I wanted to touch on as far as being able to recognize this from a table of values. So notice numbers 27, 28, and 29. We have x and some function of x, f of x, g of x, and h of x for numbers 27, 28, and 29 respectively. And so the same inputs are posted, -1, 0, 1, 2, and 3, and then different outputs are given for the different functions. So our job is to determine whether the function is linear, exponential, or neither. If it's linear, let's go ahead and find the linear function that it models, and if it's exponential, find the exponential function. So if we determine that it's neither linear nor exponential, there's no further work to be done there. We kind of just get out of doing anything in addition to that. Okay, so here we go. Let's look at number 27 here. So I went ahead and made another chart for number 27 using all the same inputs and outputs. And what we want to look at here in order to determine if we have a linear or exponential or neither function is to look at the average rate of change. So that'll be basically looking at the slope of these two lines here. Okay, so what I'm going to do is in this, sorry, let me circle this right here. For these two ordered pairs being -1, 3, and 0, 6, I'm going to find the slope and put it here. Now for the next average rate of change, I'm going to use these two ordered pairs and put the slope here. So hopefully that makes sense here. So if I put -1, 3, and 0, 6, those two ordered pairs in the slope formula, I will get a slope of, for this first one, it'll be a 3. These next two ordered pairs, 0, 6, and 1, 12, give me a slope of 6. Ooh, so right away, the average rate of change is not constant. Okay, so that's something to look at here. But we'll want to see if the if it's not constant, then that means it's not going to be linear. But we want to look a little bit further at the ratio of the consecutive outputs, because if the ratio of consecutive outputs is constant, then we can say that it's at least exponential. So continuing here, the average rate of change for, let me do the next, these two ordered pairs will give me 6 again. Interesting that it's the same as the previous. Now what happens if we do these last two? So the slope of the line that goes through 2, 18, and 330 will be 12. Okay. Now what's the ratio of consecutive outputs? Well, from 3 to 6, it'll be 2, right? 6 over 3, it'll be a 2. 6 over 6 will be 1. Excuse me, hold on. Sorry, we're looking at consecutive outputs here. So 6 over 3 will give me a 2. 12 over 6, rather, gives me another 2. 18 over 12 will give me a 3/2. And a 30 over 18 will give me a 5/3. Sorry, let me give you a little bit of explanation. 6 over 3 is how we're getting the 2 here. 12 over 6. I want to show my work compared to what I have in my notes, just to give you guys little added explanation on where these numbers are coming from. 30 over 18. Okay, great. So notice that the average rate of change is not constant. So in this regard, it's not linear. Not linear. And since you notice that the consecutive outputs ratio is not constant either, so it's not exponential. So it's neither. Big fat neither for this one. Okay, cool. Now let's do the same thing for the average rate of change for this next chart right here of xg of x, and I'll just go ahead and put the values in. So starting here, you'll notice that the average rate of change here is 3. It's 3, 3, and 3. What? Since the average rate of change is the same for all these consecutive inputs and their corresponding outputs, then we get to say it's linear. Okay, we could actually stop there. If you wanted to fill out the ratio of consecutive outputs, it'd be 5 over 2 here, 8 over 5 there, 11 over 8 there, 14 over 11 here. Whatevs. We don't really care about this because we already determined that this was linear since those are all constant in this average rate of change column. Okay, so then seeing that we have the rate of change or slope being 3 and the y-intercept appears to be at 5, this is y equals 3x plus 5 is the or g of x, I guess we should say, g of x. It's a linear function. That was a quick fix there. Cool. All right, we went on to the last example in this ilk. Again, average rate of change. Just go ahead and trust me on this one. For these first two ordered pairs, the average rate of change is 3/4. Oh, whoops, let me be consistent here with my 3/4, then it's 3, then it's 12, then it's 48. My goodness. So, but is the ratio of the outputs, is that going to be doing something interesting? So 1 over 1/4, that's a ratio of 4. 4 over 1, that's a ratio of 4. 16 over 4, 4. 64 over 16, that's 4. Wow, so the ratio of consecutive outputs being constant, sorry, my handwriting is terrible. Constant here means exponential. Oops, sorry, I'm getting ahead of myself by putting the exclamation point before I put the superlative. Exponential. The exclamation there. Okay, so how do we determine what the function's value is there? Well, this right here will tell you what the base is, a, so this is your a value, and the y-intercept, this value here, will give you your c. Okay, so it'll be h of x equals c, which is a 1, no big deal there, 4 to the x power. You could have it 1 times 4 to the x power, but why would you? That'd be silly. Okay, so there we go. And it is indeed exponential. Cool. So again, just as a little recap for the set, looking at the average rate of change, and if you find that it is constant as you check the consecutive inputs and their corresponding outputs, then you have a linear equation, and you can find the function's equation by taking that average rate of change value and have that be your slope, and grab the y-intercept to boot. Y equals mx plus b, or g of x, or whatever the function's name, equals mx plus b, and that'll do it. If you notice that you don't have the average rate of change being constant, but the ratio of consecutive outputs is, then you have something that's exponential. And you can take the value of that ratio and have that be your a value, so the base of the exponential, and then the multiplier out in front will be your y-intercept. So in this case, it was just a 1, so it didn't really play very much of a role there. But there you have it. Okay, cool. Now let's look at some features of exponential functions, whether the base is positive value greater than 1, or if it's a positive value between 0 and 1, so being a proper fraction. We're going to have different shapes, not shapes necessarily, but directions in which the trajectory is traveling. Either it's going to grow exponentially, or it's going to decay exponentially if you have your a value being greater than 1 or between 0 and 1 respectively, okay? So other features that exponential functions have is that they do not have x-intercepts, and they have a y-intercept at 1, provided that they don't have any stretching, or sorry, not stretching. Stretching won't do that. If they don't have any shifting, then the it's always going to be at 1. Oh, yeah, actually, if you have stretching or compressing, you'll have that y-intercept happening either a little bit larger or smaller, depending on what the c value is, if you have one. But you know, these parent functions that are being mapped out here, they do not have a c value other than 1, and they have a base of a. That's the thing that we want to focus on here. So with exponential functions, there are 3 points that are critical to plotting, and that'll be the points of 0, 1, which both, if you're dealing with exponential growth or decay, is always present. Now, if you're dealing with exponential growth, so your a value is greater than 1, then you can plot the values -1, 1 over a, whatever your a value is. And then there's also, on the other side in quadrant 1, there's the ordered pair 1, a. So these 3 points can always be plotted, and 2 of them depend on your value of a. And that's also true if you have exponential decay. So since the a value in exponential decay scenario here is going to be a proper fraction, then taking its reciprocal is going to make a value larger than 1 as the output here when your input is -1. And then smaller, of course, than 1 because your a value is proper fraction. What else can we say about it? Well, there's some information talking about limits and asymptotes and that sort of thing. It's always y equals 0, okay, which has nothing to do with whether or not you're dealing with a proper fraction or a value greater than 1. It's always going to be that horizontal asymptote is happening. It just depends on what direction you're going to be approaching that horizontal asymptote will depend on your a value there. And if the graph is smooth and continuous no matter what, there's no corners or gaps. Either you are growing exponentially as you increase your values of x, or you are decaying exponentially as you increase your values of x. It'll all depend on that a value, the base of your exponential expression in your exponential function. So let's go ahead and expand what we've just kind of had a little overview on in regard to these graphical representations, and let's match them up to their exponential equations. Okay, so here we are. For number 35 through 42, we are given graphical representations of some exponential functions, and we want to look at them, see where they cross, get an idea of their trajectory behaviors, and that'll tell us which equation they should match up with. So looking first at number 35, I'm going to match that up with equation B. Now, why would I match it up with B? Here, let me put a B there. Well, I'll notice that I have a negative 1 as a multiplier in front of the x. So it's like you have your y equals 1/3 being the base is another way that you could write it, because 3 to the negative 1 power is the same as 1/3. You're taking the reciprocal of that base of 3. And 1/3 is between 0 and 1. So it's very much akin to what's going on with the parent function. The a being between 0 and 1. Okay, so that'll be my b. Looking at number 36, that one is like f. And why is that? Well, you'll notice that this one's markedly more challenging. It's a horizontal shift of 1 unit to the right. Yep, that's how I would categorize that. Now that might be a little bit hard to see, but because it's crossing at less than 1, and otherwise it has the same shape as the parent function of the exponential in which a is greater than 1, we're good to go on that one. Okay, cool. So for 37, it looks like it is akin to what's going on in D. Now D is this one right here, where we have a reflection over the over the x-axis by virtue of the multiplier being a negative 1, and also we have a negative sign in the exponent, a negative 1 in the exponent. So it's like the base is 1/3, but it's being flipped over. Okay, so that'll most likely match up with what we're going on and seeing in number 37. Number 38, this is a reflection over the x-axis again, and it looks like it's shifted up by 1. So we've got that looking like H, I would say, right here, this one. Okay, just a moment. I'm getting a phone call and I'm going to need to answer that. Sorry. Press pause. Okay, thank you for your patience. I'm back. So looking at number 39, it looks like we have exactly the parent function, if I'm not mistaken, in which a is greater than 1. So I'm going to liken that to what's going on with a's function, y equals 3 to the x power. We cross at 0, 1, we have that exponential growth happening. It looks very much like the parent of f of x equals a to the x powers, where c of course is a 1 and a in this case happens to be 3. Okay, so for number 40, it looks like we have the parent in which a is greater than 1, but it's reflected over the x-axis. So that's going to be looking most like, as far as the function's concerned, c. Negative, y equals negative 3 to the x power. So I'm going to save that one C. And number 41, it looks like we have that parent in which a is greater than 1, but it's shifted down by 1. So which function does that most look like? Looks like E to me. There we go. Number 42, it looks like we have pretty much the parent of exponential function in which we have the proper fraction value for a. So a is between 0 and 1, so it's like, doing that decay business, but it's shifted 1 unit to the right, and that's why the y-intercept is all the way up at 3. Okay, so which one does that most resemble as far as the functions are concerned? That would be g. So think of g as the exponent being factored by a value of -1. So if I pull out a value of -1 from the exponent, it would be -1 times the quantity x minus 1. So that makes the 3 base value turn into a 1/3 by virtue of the -1 factor being pulled out, and the leftover stuff was x minus 1. That is horizontal shifting 1 unit to the right. Okay? Cool. So hopefully that makes sense, but we could talk about more in class if you like. I would like to kind of more or less glaze over the most famous exponential base that there is. So we've been working with bases so far of 2 and 3, but there's actually a base number that comes up in models for financial phenomenon or natural processes of exponential growth and decay. And this base, when you try to do model fitting, it comes up so often that it is its own constant number. And I'm talking about the Euler number. What else does it? It has all these other names to it. It's Napier's number, or Napier if you're pronouncing it in the French way, which is more accurate. There are a few different mathematicians that it gets attributed to, like Bernoulli, but the most recent contributions to the idea of this number were done by Leonard Euler. And yes, this is pronounced Euler. I actually have a funny story about the pronunciation of, it's not, I mean, it's kind of funny, but sad at the same time. We could talk about it in class if you want to. I don't want to waste time here. In any event, it's just a number, this Euler number. It's an, what's it called? It's an irrational number, like the decimal expansion goes on forever and ever and ever without any pattern. It's approximated, as you can see right here, okay? And if you're interested in like the history of the number and its derivation, you can click on this hyperlink right here on the word here. So you see how it's blue where my cursor is, and the hyperlink works in the PDF file as well. Okay, now it's defined as follows, as the limit as the quantity 1 plus 1 over n, all collectively raised to the n power, is the limit of that output as n approaches infinity. That's going to give you this value e. Again, I'm not going to get into the derivation of this, like how this comes up. If you're interested, you can click on this link and then also do your own research. It's beyond the scope of this course to talk about the derivation of this number, but it's a famous base for exponential modeling. And it'll come up in exercises that you'll get into with some applications, but for our purposes, we're going to focus more on solving exponential equations, which are equations that have your variable that you want to solve for stuck up in the exponent realm. So how do we deal with that? We want to use this relatively, and probably new to us, rule. Maybe some of you have been introduced to this rule already. It basically says if you have exponential expressions set equal to one another and their bases are already equal, then their exponents necessarily have to be equal to each other. So you can kind of like cross out the bases and let the exponents be set equal to each other, and that'll allow you to solve for the variables that could be living in the exponent. So we have a few examples in which we want to tackle here, and I want to show you the trick. The trick to solving exponential equations rather, is to make the bases the same. So find the common base is the mantra here. So I'm going to write that up top. Okay, so you're looking for, among the current bases for number 73, that's the first example that we're going to go on to, among the bases 8 and 16, can they be rewritten as some exponential expression with the same base, right? Because we can't write 8 as something raised to some power such that it equals 16, right? No, the double of 8 is 16, but we can't rewrite it in an exponential way such that these bases could be equal to each other, and vice versa. However, 8 and 16 can both be rewritten as base 2. Base 2 is going to be the hot thing right here. So rewrite 8 as 2 to the third power, and then it's going to be further raised to the negative x plus 14 power, right? So you can even put some parentheses around that just to make it super clear that that whole thing is the collective exponent. On this rewritten, 8 is now 2 to the third power, 16 is 2 to the fourth power, and then it still has to be raised to the x power. We have to address that x exponent in just a second. Then you can use this 3 and distribute it over that exponent there, multiply these exponents here, and we will get 2 to the negative 3x plus 42. So that's distributing that 3 over this quantity here is equal to 2 to the now 4x power. Oops, sorry, 4x is what I meant to say, not 2x. All right, 4x. Now that the bases match and everything in the exponent space has been simplified, we can actually cross out those bases and set the exponents equal to one another. Negative 3x plus 42 equals 4x. And now it's like, couldn't be easier as far as solving this equation. We're going to add 3x to both sides. It's going to be 42 equals 7x. Divide both sides by 7, and you're going to get x equals 6. Final answer there. Okay, let's do that again for this next problem, number 78. It's going to be a little bit more challenging, but we're going to want to start off with the same mantra. Let's get the same base going. 9, 27, 3, these bases, they're not all the same, right? But if we forced them all to be the same, i.e. the collective base here would be 3, base 3. It's going to be the same base that we're going to want to force here. Okay, so let's rewrite 9 as base 3, so that'll be 3 squared. Still, it needs to be raised to the 2x power, and that's multiplied by 27. Rewrite that as base 3. Well, 27 is 3 to the 3rd power, and then it's still raised to the x squared power. And then this on the right-hand side, it's already base 3, so just kind of leave it there, okay? You're multiplying exponential expressions in what we've written here that have the same base, but wait, hold on. Actually, let's multiply. Let's use a little bit of power rule first, and then we'll use the product rule. We should do these things in a correct and smart order. 3 to the 3x squared equals 3 to the negative 1. Okay, so we're almost to where we want to go with it before we cancel out the bases. We're not quite there yet. We need to use the product rule to add these two exponents together. And that'll look like 3 to the 4x plus 3x squared equals 3 to the negative 1 power. Now we have exponential expressions alone on both sides of the equation, in which case we can actually cross out those bases and set the exponents equal to each other. And that'll look like 4x plus 3x squared equals negative 1. Now I know what you're thinking. Oh God, can I have this x squared term as the leading term? Yes, of course. So go ahead and switch the positions of those and add 1 to both sides. So you'll get 3x squared plus 4x plus 1 equals 0. Now we have a quadratic equation set equal to 0, and we could certainly solve for that. So you can always opt for the quadratic formula, or if you notice that this can be factored, by all means do so. So I'm just, in the interest of time, going to go dot, dot, dot. It can be factored, and it would be factored into 3x plus 1 times x plus 1 equals 0. 0, which means that x either equals negative 1/3 or negative 1. So there's the solution that we're looking for there. Okay, last example of this type, and then we'll go into just one more example after this of looking at a graph. So we're almost done here, folks. I know I've been talking for quite some time here. Let's just go ahead and practice this solving an exponential equation, and let's have it be base e. Very fun. We'll mix it up a little bit. So here we want to recognize what's going on over here with this 1 over e squared. We're going to use a negative exponent in order to get that to be an e, but in the numerator space. So like so. It'll be rewritten as e to the negative 2 power. Now we have exponential expressions just being multiplied together that have the same base. So we could add the exponents, which will look like this: e to the 3x plus a negative 2 or minus 2. Okay, now on either side of the equation we have exponential expressions equal to each other with the same base. Go ahead and cross out those e's and set the exponents equal to each other, and we'll get x squared equals 3x minus 2. Put everything on one side, it'll be x squared minus 3x plus 2. Can this factor? Sure enough it can, and it factors dot 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 as x minus 2 times x minus 1 equaling 0. So that means x is either 2 or 1. Cool. So that was a relatively quick style one. We just needed to recognize this negative exponential here in the reciprocal factor, and that was basically the hardest part of that particular problem. So at this point, the textbook gives you a little bit of a summary of the properties of exponential functions. So going back to the graphical representations of them, what are the domains? Well, regardless of the value of a, the domain is always all real numbers, and the range is always everything positive. Yeah, strictly positive. We can't include 0 because, y equals 0 is the horizontal asymptote. And again, I'm talking about the parent functions. The parent function of the exponential function, whether we're talking greater than 1 or between 0 and 1 proper fraction. And what else could we say? We are using the horizontal asymptote to either approach infinity or like go off to infinity, right? As we're writing the y equals 0, the horizontal asymptote here, we're either growing off into incredibly large numbers if our a value is greater than 1, or if our a value is between 0 and 1, then we are approaching 0, the horizontal asymptote in that regard. So as you can see in our summaries, we reference figures 22 and 26 again. We saw them earlier, so I just thought I'd put them here again for our reference. And then, of course, part of the summary is this little blip about exponential expression equivalence. When you have the same bases, same exponential expressions with the same base equal to each other, you get to set the exponents equal to each other. Cool, cool, cool. Now, one last example before we wrap up this lecture for the day is let's just take a look at this exponential graph and determine what the function is. So you'll notice that the y-intercept happens at 0, 1. So that's where the parent function crosses, whether you are having an a value between 0, 1 or greater than 1. But notice that we are definitely exhibiting exponential growth here, because as x gets larger, so does the output. Okay, so we definitely can see that a is greater than 1. That's definitely happening. And look at the other two plotted values. That'll give you another clue as to what the a value is specifically. So notice that at -1, we have a 1 over 5, which looks a lot like 1 over a, doesn't it? Doesn't this look very much like this? I mean, the curve is much more severe, but it has the same qualitative nature to it here. It's exponential growth. We have at -1 an output fraction of 1 over 5, which it looks like will be the a value. Check the other point, and yes, you will find that 1 comma a in this case is 5, so that means that our function is f of x equals 5 to the x power. Okay, I know I have it in that weird celestial print marker color there, but yes, and we also notice that we have a horizontal asymptote at y equals 0, so there's no vertical shifting, and there seems to be no horizontal shifting either, because we have that y-intercept happening at the quintessential point associated with the parent function of the exponential, in which we are exhibiting growth where a is greater than 1. Okay, so hopefully that was a good enough overview for us to feel comfortable getting started on the homework. But if there are more things, specific examples that we would like to talk about, or things that come up in your homework that didn't get presented here, by all means ask to see those very items in our class time. We can go into more detail there. Okay, that's it for today. Thank you so much for your attention.